Hello students, so for your NEET we are today going to discuss thermal physics in brief, and we'll try to cover all the important concepts for this chapters or set of collection of chapters which will prove to be beneficial for you. So let's see one by one what we have in thermal physics. So thermal physics is divided into different parts, starting with thermometry where we measure temperature, then we have calorimetry where we measure the amount of heat, then next we have thermal expansion where we see the effect of heat, how it changes the dimensions of any object and also changes the density, whether it be solids, liquids or gases. Then after that we will see the concepts of heat transfer, how heat can be transferred or energy, heat energy can be transferred from one object to other. So let's start. So as I said, first we see about thermometry where we study the measurement of temperature, which is done obviously with the help of a thermometer. And when we use thermometer, what all types of questions we will get from this chapter? Thermometry, you will be seeing the usage of the following formulas. One is whenever we compare the temperature in different scales. So when we have any scale, you should remember for any temperature scale, whatever temperature you are measuring by that scale theta minus, there we take two standard or reference temperatures which is called as lower fixed point and upper fixed point. So this value is same for all scales. For every scale this value will be same. So LFP, lower fixed point, we generally take as melting point of ice, and upper fixed point we take as boiling point of water. Now you know in Celsius it is 100 and 0 degree Celsius. If you have a Reaumur scale, it is 80 degree Reaumur and 0 degree Reaumur. If you have Fahrenheit scale, it is 212 degree Fahrenheit, and this is how much? 32 degree Fahrenheit. So there are different scales. For all the scales you have to remember that this is going to be the same, right? Now when we are comparing temperatures, we will use this formula. Second formula which we have, if we wish to compare temperature change, which we will denote as delta theta, for different scales, instead of the numerator part theta minus theta LFP, you will just use delta theta. Denominator will be same, upper fixed point minus lower fixed point, and this value is same for all. So just we will take an example for both so that you understand how we are going to use this. Example, if they say (20 degrees Celsius) will be equal to how much in Fahrenheit. So what we will do, just use this, theta is 20, lower fixed point for Celsius is 0, upper fixed point is 100, lower is 0. That's it. Here you will write, in Fahrenheit we have to write theta F. So theta F minus lower fixed point of Fahrenheit is 32, upper is 212 minus 32. From here you can get the value. Clear? Next, if we see for temperature difference, if they say temperature change of 20 Celsius corresponds to what change in Fahrenheit, Kelvin and R, which is Reaumur scales. So if they ask you that we have a temperature change of 20 Celsius, so what change will it correspond to in Fahrenheit, Kelvin and Reaumur scales? Well, this also we can do it very easily and very quickly. How? See here, this formula, just we will use now delta theta. They are asking of change. So in Celsius it is 20. Upper fixed minus lower fixed point in Celsius is, as I said, 100 minus 0. They are asking in Fahrenheit, so we will write delta theta F. Now in Fahrenheit we saw it is 212 minus 32, which will be 180. When we see Kelvin, we will write absolute scale delta theta K, 373 and 273 Kelvin. And when we write in Reaumur delta theta R, Reaumur higher is 80, lower is 0. So from here you can get the corresponding temperature difference in all the scales. I hope this is clear to all of you. A simple technique but very effective one. Moving on, next important formula that we have is for absolute scale or for Celsius scale. Two important types of scales are there. Absolute means in Kelvin, Celsius, so you already know. So when we are taking these two scales, what we use to make a thermometer is what we call as thermometric property of a substance. So we have a term which is called as thermometric property of a substance to make a thermometer, which is denoted as X. So X is nothing but it is a function of temperature. Suppose I am taking temperature as T. Generally we prefer linear functions or linear functions. Generally we take X is a linear function which is of the form AT plus B. For example, length of mercury column, you have length of mercury column in clinical thermometers, you have resistance of a platinum wire in electrical thermometers you can use. In constant pressure and constant volume gas thermometers we can take pressure of gas, volume of gas, these all can be taken as thermometric properties. P gas at constant volume of ideal gas, V gas at constant pressure of ideal gas. All these are such properties which vary linearly with temperature, so we use this. So when we have Celsius scale, any thermometric property, this will be of the relation X at any temperature T minus X at, since Celsius scale we are using, at 0 degree Celsius by X at 100 degree Celsius minus X at 0 degree Celsius will be equal to directly T upon 100. That's it. Xt minus x naught by x100 minus x naught is equals to T by 100. So this relation we are going to use. Xt is the value of x at T degree Celsius, this is at 0 degree Celsius, this is at 100 degree Celsius. Whereas when we use in absolute scale, which is also called as Kelvin scale, so x is directly proportional to temperature. We have a straight line passing through origin because we take temperature in Kelvin. So 0 Kelvin, all the thermometric properties become 0. So what we do over here, we take Xt by T is equals to, we take another standard temperature as triple point XTR by TTR. Triple point of water which is taken as 273.15 Kelvin around. So this we take as the standard value. So if you know the thermometric property value in the question, they will mention at the triple point of water, then that will ask at any other temperature, this temperature is in Kelvin. So you can use this formula Xt by T is equals to XTR by TTR. So you have a straight line graph passing through origin. Whereas in Celsius scale, the graph is a straight line, but it won't be shown to pass through origin because we are taking in Celsius. So when we are taking like this, we can see this is x naught at 0 degree Celsius, this is x100 at 100 degree Celsius. So you can compare any two. Clear? So very, very important formula. One quick question we will take on this so that you understand. Like we have length of mercury column in ice at 0 degree Celsius, suppose it is given as 5 centimeter, and in boiling water they have given say 10 centimeter. Then length of mercury column in a liquid is say 8 centimeter. What is temperature of liquid? Simply they ask this thing. So what we can do from here, directly use L theta minus L naught by L 100 minus L naught is equals to T by 100 I said, so theta of the liquid by 100, that's it. So L theta they have given, it is reading 8 centimeter. At 0 degree Celsius it was reading 5 centimeter. At 100 degree Celsius it is reading 10 centimeter. So we can easily find theta of the liquid will be 8 minus 5, 3 by 5 into 100. So 300 by 5, which is 60 degree Celsius. I hope it is clear to all of you. Now we move to the next section, which is what we call as calorimetry. Now in calorimetry, we measure the heat required to change the temperature or change the state. These two important conditions are asked. So when we have to change temperature where the state will remain fixed, the amount of heat required delta Q is m integration of S dt from T initial to T final. S is called as the specific heat capacity, and if S is constant, you can directly write it as ms delta T. Okay. Now here there is no change in state, that time we are using the term called specific heat capacity. Understood? In such case, remember one thing, if rate of heat supply, suppose P is fixed, so we can write P as dq by dt, which is also dq can be written as ms dt, mass into specific heat into change in temperature by time, this value. Now this ms, mass into specific heat, we also call it as sh, which is called as thermal capacity or heat capacity. Kindly be aware of these two terms, thermal capacity and specific heat capacity. Just S is specific heat capacity, sh is thermal capacity. So in this case, if P is constant, this is fixed. So you can see from here, we draw what is called as a heating curve. If you keep on giving heat with time, if you are continuously giving heat, so temperature will change. So temperature changes with time. So here what we can see, the graph you will get like this. Now if you see the slope of this graph, delta t by delta t is also equals to, because it is a straight line passing through origin, so it is also equals to dt by dt. And what is dt by dt? Dt by dt is P by ms. So it is inversely proportional to the thermal capacity. So slope will be inversely proportional to thermal capacity, and if mass is same, then we can say the slope will be inversely proportional to specific heat capacity. So from here we can get the specific heat capacity also if two different graphs are to be related. Understood? So they ask question like, they will give you that there are two substances, heat is supplied at constant rate, and they ask you that mass of both the substances are same, m1 is equals to m2. So what we can see, which one has more slope? Slope of one is greater than slope of 2. So thermal capacity of 2 will be greater than thermal capacity of 1. Thermal capacity is m into specific heat, so mass is same. So from here specific heat capacity will be more whose slope is less. So this type of questions be aware of. So this is when we are changing the temperature. Now next thing comes what we call as if state changes. So at that time temperature is constant. So temperature becomes constant at that time. So if state changes, then we directly use delta Q is equals to m into L. L is called as latent heat. This latent heat is of two types. One is latent heat of fusion, one is latent heat of vaporization. Latent heat of fusion we use during melting, and LV we use during boiling, liquid to gas. So LF and LV, two important values which we need to remember. LF when we have ice converting to water or water converting to ice at 0 degree Celsius, this value is 80 calorie per gram. When we are taking LV, latent heat of vaporization, it is 540 calorie per gram for water getting converted to steam at 100 degree Celsius, and sometimes we use it for water to water vapor also. Water to vapor even at triple point theta TR, which is approximately 0.15 degree Celsius. There also we use this. So latent heat is only to be used when there is a state change. Now in this case, if again we talk of power, the heat supply, if we write it as dq by dt or del q by del t, if it is fixed, then both the rates, instantaneous and average rates, will become same. Instantaneous and average rates become same, so we can write it as mass into latent heat by delta T. So mass by delta T into latent heat. So from here if P is fixed, so you can see that delta T will be proportional to ml. Time taken to change the state, we can see it will become proportional to ml. So when we have heating curve during state change, there is no change in temperature. So temperature is constant. So temperature is constant, and here we have time. So in this case, we can see if you find the area, this time is suppose delta T. If you see this thing, this area, here temperature is constant. So when temperature is constant, what we can say that the heat supplied rate, if is P into delta T, this will become the total heat delta Q, which will become equals to ml, mass into latent heat. So P delta T is equals to mass into latent heat. From here we can find the time. So time will be ml by. So or you can say that if two different substances are given to be compared, that which has more latent heat, which has less latent heat, you can directly compare from here. Just see the times. So whichever has more time, that will have more latent heat, provided the masses are same. Okay. So here these are two important things. One quick question we can take from here so that you understand the difference between the two. Suppose we have a substance which is undergoing temperature change, and here the substance is in solid state here melts, here it is in molten state, temperature is rising, here it boils. Now this time we are taking as T1 and this time we are taking as T2. In question they have given theta 1 is greater than theta 2 and T2 is greater than T1. Compare specific heat of solid and molten states and latent heat of while melting or fusion and latent heat of vaporization. So now see, power, rate of heat supply is given constant. So if power is given constant and we have to compare this. So what I said, see here, mass is same substance is going that change. So we can say from here slope which is tan theta and theta 1 is given greater than theta 2. So therefore slope 1 greater than slope 2. So specific heat of 2 will be greater than specific heat of 1. So specific heat of 2 is nothing but molten state. So S molten and this is S of solid state. Also when you see the melting and boiling cases, we have to compare time. T1 is greater than T2. For T1 I said time is proportional to ml. Mass is same, T1 greater than T2, so mass into latent heat of fusion is greater than, I'm sorry, in question we have given T2 is greater than T1. So let's interchange here. So we will say T1 and T2. T2 is more, so MLF is less than MLV. So latent heat of vaporization will be greater than latent heat of fusion. So in this way we can answer this question. I hope it is clear. Next, when we have something called water equivalent. W of a substance, you just need to replace that substance by water. So you will just replace that substance by water. So what we write is, if you write delta Q is heat required to mass of a substance MS specific heat SS, you are changing its temperature by delta T. So if you want to replace it by water, so you can replace it by W SW delta T. So from here W can be written as MS into SS by SW. So you basically replace that substance by W mass of water, but only during temperature change. So MS mass of substance is equivalent to W mass of water, but during temperature change only, not during state change. So during temperature change you can replace MS mass of substance by W mass of water. So if water equivalent is given, you can directly use this formula. Clear? Now one more important thing that we should be clear with, which is called as principle of calorimetry. Whenever we are mixing substances in a closed vessel, then sum of total heat gained is equals to sum of total heat lost, till all attain same final temperature. Whenever we are writing gained heat, kindly remember, if you are changing the state, then we know that heat is gained when you melt a solid or you boil a liquid. On the reverse, if the liquid freezes, then that means it is leaving out heat, it is losing. And when steam or say gaseous state is converted to liquid state, there also heat is lost. Whereas during temperature change, if temperature rises, you write gain. If temperature falls, you write loss. Now gained and lost are never written negative, they are always written with magnitude. Whenever you are writing gain means you will write theta final minus theta initial. Whenever you are writing loss means theta initial minus theta final. Whenever you are taking during temperature change, I am saying, you will always use mass into specific heat. Gained means temperature is increasing, so T final minus T initial during temperature change. And whenever we are writing loss, you write MS T initial minus T final. We always take the magnitudes and equate it on both sides. Clear? Now here one important and interesting case comes. If no change in state occurs, for such problems there is a shortcut. T final of the mixture, you can directly use summation MS T initial by summation MS. Directly you can go for such problems where we have final temperature of the mixture is equals to summation MS T initial by summation MS. For example, if we have A 10 gram, or let's take like this, mass is M, specific heat is 2S, temperature is T naught. B, we have 2M mass, specific heat S, temperature is 3 T naught. C, we have mass is 3M and 3S and temperature is 4 T naught. These are mixed. So we will say T final of the mixture, directly use this formula, multiply MST. So first we have 2MS T naught plus 6MS T naught plus 4 3s are 12, 3s are 36, 4 3s are 12, 3s are 36 MS T naught divided by product of MS, 2MS plus 2MS plus 3 3s are 9 MS. So all MS cancels, 36 6 42 to 44 T naught divided by 9 and 2 11 to 13. That's it. One more thing they ask in such questions which you have to remember, they will ask you equivalent specific heat of the mixture. If they ask you equivalent specific heat of the mixture, so in that case what you will do, directly go by summation MS by summation M. So summation MS, if they give you two or more substances being mixed, so if they write you that two or more substances are getting mixed, so you can use summation MS by summation M. But it would be better that presently we leave this because we will again discuss this thing in thermodynamics. So let's not confuse you with that concept presently. Just focus on here that if there is no change in state, directly T final of mixture is obtained by summation MST by summation MS. That part we can see later in next class when we will study about thermodynamics. There we will see that. Okay. Now apart from this, suppose you get questions where state is also changing, right? So how we use calorimetry, principle of calorimetry, just like we will take one question over here where we have say a vessel whose water equivalent is given say as 5 grams and it is already containing some water. Let's take this water as 55 grams and these two are at say some temperature 20 degree Celsius. So they give you in question that steam is passed, suppose x gram steam is passed, final temperature becomes 80 degree Celsius. So we have to find how much steam was passed. So if you solve this question, now you can see that final temperature is 80, so steam cannot exist, so steam will get converted to what? Water. So you can clearly see that who has gained heat and who has lost heat. The temperature 80 is obviously less than 100 degrees Celsius, so steam is passed. Obviously the steam temperature we are taking at 100 degree, final is 80. Water and calorimeter or vessel both had initial temperature 20, final became 80. So they have gained heat and this steam has lost heat. So delta Q gained by vessel or calorimeter, I am using the term calorimeter, this is also used, vessel or calorimeter plus water, they have gained, and who has lost? Delta Q lost by steam. Now when you see vessel plus water, how much heat they had gained, so you will say mass of water plus, since they have given water equivalent, so you will take that of the vessel. So total mass you can take as MW, mass of water plus water equivalent. Now both are treated as water only, so specific heat of water. Water is not undergoing any state change, only temperature change. Initial temperature 20, final 80. So I said gained means final minus initial. So I will write 80 minus 20. Now if you see steam, first what it has to be done, steam x gram, first it will condense. So when it will condense so you will use mass into latent heat, and after condensing from 100 it has to come to 80. So it has become water. How much water? X gram only. So x into, it has become steam. So x into specific heat of steam, and from 100 it has to come to 80. So solving this, we know specific heat of water 1 calorie per gram per degree Celsius. This value is already given, 55 plus 5, 60 grams, and latent heat of vaporization 540 calorie per gram. Specific heat, I'm sorry, not of steam, extremely sorry for that, water. It has become water here, very sorry for that. Specific heat of water is 1. So once you put the value, you will get the value of what we call as X, right? So after this, let's move to the next section, which we have is of thermal expansion. Now in thermal expansion questions, you need to be aware of that if solids are given or liquids are given or gases are given. In solids, thermal expansion is very small, so we use concepts like binomial approximation, small approximations are used. So whenever we have thermal expansion in solids, we have thermal expansion to be very, very small. So if it is very, very small, so we can use approximations like 1 plus x to the power n, approximately 1 plus nx. If we use n, can be plus minus whatever. If you have here minus sign, here also you can put minus sign. X is very, very small than 1. Then you can use cases like if y is proportional to x to the power n, then percentage or fractional change, directly multiply the powers. Percentage just multiply by 100. This is called fractional change. If you multiply by 100, you will get percentage change. This can be used. When you see terms like 1 plus x1 by 1 plus x2, like this term, you can directly solve and get 1 plus x1 minus x2 approx. When you see terms multiplied, you can directly add. So these are some approximations which can be applied for solids. Clear? Now in solids, we define 3 terms we know, alpha, beta and gamma. 3 coefficients we define, where alpha is defined as change in length per unit length or fractional change in length per unit change in temperature. Beta, we use it for surface area, delta A by A delta T, and gamma we use delta V by V delta T. Okay, so here when they ask you free expansion or delta L, we can directly write L alpha delta T, and similarly delta A we can write A beta delta T, and delta V change in volume is V gamma delta T. Okay, now when we have isotropic solids, so alpha will be same in all directions. So alpha fixed in all directions. So in that case, gamma we can take as 3 alpha and beta we can take as 2 alpha. So whenever we are dealing with isotropic solids which have same physical properties in all directions, so whatever direction expansion is possible, there you will take same alpha everywhere, and you can use gamma as 3 alpha, beta as 2 alpha. This is one very important concept, kindly remember this. Now if it is not a isotropic solid, if it is an anisotropic solids, so if you take different directions in space, so we have three possible directions x, y and z. So for all expansions taking place along x axis, y axis and z axis, we can see that these three are unequal, then gamma of a voluminous object you will use as alpha x plus alpha y plus alpha z. Beta, whenever you are seeing expansion in xy plane, for expansion in xy plane area or surfaces which are kept in xy plane, you will take beta as alpha x plus alpha y. For all expansions taking place in yz plane, you will take alpha y plus alpha z. For all expansions taking place in xz plane, you will take alpha x plus alpha z. So these are to be used for anisotropic solids. Isotropic solids, it is just like photographic enlargement. Remember this thing, when we have isotropic solids, since alpha is same, it is just like you zoom in or zoom out a photograph. So this is just like a photographic enlargement. Any two points you take on that, fractional change in separation between any 2 points of such an object, whichever 2 points you take, the fractional change is the same and equal to how much? That fractional change in any separation will be alpha delta theta or alpha delta t, whatever you are taking, temperature change delta theta or delta t, so alpha delta t. This you will use. Remember, fractional change in separation between any 2 points of such object. Okay. Now next thing, if we see the applications of thermal expansion, when we have alpha, if in a rod you see that it is given as a function of x, if alpha is given as a function of x, suppose we have a rod and this is taken along x axis, this is taken as x equals to 0, and at x distance if you come, alpha is variable, so we can find the equivalent alpha of the rod as integration of alpha with respect to x from 0 to L. Suppose the length is L, so 0 to L and divided by total length. So if they say what is the change in length if temperature is changed, so you can write L alpha equivalent delta T. This is to be used. And this thing, if you use for combination of rods in series, like example, we have L1 alpha 1, L2 alpha 2, L3 alpha 3. So this same formula which you wrote in integration, you will just write it as you are multiplying alpha with length. So here also alpha 1 L1, alpha 2 L2, alpha 3 L3 divided by total length, which is L1 plus L2 plus L3. So directly you can go with this case. Understood? There is an important question on this example. In a rod, alpha varies linearly from alpha 1 to alpha 2. Find alpha equivalent. So if they ask you what is alpha equivalent, so what we can do, see, alpha equivalent is integration alpha dx. Now they have said that alpha varies linearly, so we can directly solve by one simple method, which is a graph. If you see alpha versus length, they have given that it is varying linearly. So suppose here it is alpha 1, and when the length becomes L, this becomes alpha 2, right? Now let's see how we can get the answer quickly for this. If you write alpha equivalent, it is integration alpha dx 0 to L by L. But do we know that the meaning, geometrical meaning of integration is nothing but area under the graph? So you just need to find area under the graph from 0 to L and divide it by L. So what is area? This is a trapezium. So for trapezium, you know, area under a trapezium is half sum of parallel sides. This side is alpha 1, this is alpha 2. So alpha 1 plus alpha 2 into, this is how much? L, and whole divided by L. LL cancels, so it is alpha 1 plus alpha 2 by 2. Or in general, directly we can remember this as shortcut, that if anything varies linearly, the equivalent value is nothing but the average of the two minimum and maximum values, alpha 1 plus alpha 2 by 2. Directly also you can remember, if anything varies linearly. If non-linear variation is there, you will have to integrate. And if you have a combination of rods like this, discrete rods, so you can directly use this formula. Clear? Let's move. Now, after this, next thing which we have to remember in case of solids, talking of solids, so density, we know that density is mass by volume, so it is proportional to V to the power minus 1. Now I said that in solids changes are very small, so I said that whenever powers are there, directly you can say delta rho by rho will be minus delta V by V. But what is delta V by V? Delta V by V is gamma delta T. So we can say delta rho is equals to minus rho gamma delta T, where rho you can take any, suppose initially rho naught, delta rho is rho any other temperature T minus rho naught. Okay, so this is rho naught at a temperature T naught. Delta T means T minus T naught. You can directly use this. So in case of solids, you can approximately use rho T is rho naught 1 minus gamma delta T. Not for liquids and gases. For solids you can use this thing. Next thing, when we have solid some applications, we have something which is called as a bimetallic strip. When we have a bimetallic strip made of two metals, now these are riveted at the ends so that they can expand or contract together. Initially at any temperature T naught degree Celsius, the lengths were same. Now here we have alpha 1 and here we have alpha 2. So when temperature increases at say T greater than T naught, so what will happen? Whichever has more alpha, say alpha 1 is greater than alpha 2, whichever will have more alpha, it will expand more. So due to this, this will bend. So ends are riveted, so it will bend. So the bending will be as shown. We take the width d to be very, very small than the length. So when you see the strip, so it will be having some radius of curvature. Let's call the radius of curvature as r at temperature T. So radius of curvature at T degree Celsius, if they ask you, so how we can find this? Radius of curvature, this is d. Now this length, if you see the upper one, L1T, so L1T will become, earlier it was L1 plus alpha 1 delta T, and this is L2T, which will become L1 plus alpha 2 delta T. So when you divide both, and L1T can also be written as radius into arc angle. So r plus d is the radius and multiply by arc angle phi, and this one is radius is r and arc angle is phi. So when you divide both, you will get, and take the approximation which I told, 1 plus x1 by 1 plus x2, directly on dividing we get the value of radius of curvature at t degree Celsius as d into alpha 1 minus alpha 2 delta t. So this radius of curvature is independent of the length, it is independent of the length, it is directly proportional to the width, inversely proportional to difference in alpha, and inversely proportional to change in temperature. Whichever has more alpha, it will bend accordingly. Clear on heating. Now next we have, whenever we measure error in reading by a scale. Now whenever we read something by a scale, and if the scale is metallic, so obviously it will expand and you will get some error. So in metallic scale reading, just a single formula will help you. You will use true length of an object at any temperature theta degree Celsius is equals to scale reading of the object at theta degree Celsius, what the scale is reading, and 1 plus alpha of the scale into theta minus theta c. Now what is theta c? Theta c is called as calibration temperature of the scale. Calibration temperature where scale reads correctly. So where the scale will read correctly, that calibration temperature, if you are using at any other temperature, then you will get there is a difference. So error is nothing but true minus scale reading, the difference. So basically we will use a symbol to show difference, whichever is bigger minus smaller, true length minus scale reading or scale reading minus true length. So that will give you, so from here you can use. Now sometimes true length of object at theta degree Celsius, we can write it as true length at calibration temperature theta c into 1 plus alpha of the object into theta minus theta c. So we have this relation. Now you can use it in any way. Okay, so L true theta c into 1 plus this value is equals to scale reading at theta into 1 plus alpha scale into theta minus theta c. So this expression we can use directly in questions. Okay, next we have error in time reading by clock. If it has a metallic pendulum, then in that case we know time period is proportional to root L. So delta t by t can be written as half alpha delta t. Why? Because power you can see is this. So you can write this in one line, L to the power 1 by 2. In pendulum we know time period is proportional to L to the power 1 by 2. So half delta L by L. And what is delta L by L? It is alpha delta t. Delta theta. Suppose temperature we are taking delta theta. This is fractional loss or gain in time. So you can use, and just use mod so that you don't have any confusion regarding the sign. So this is per second. Now what is delta theta? Delta theta is theta minus theta c. Theta c again is calibration temperature, where the clock will give correct reading. So calibration temperature theta minus theta c, this will be, so if you use the clock at temperature greater than calibration temperature, theta is more than theta c, so what will happen? Time period will increase. Time period will increase, that means it will take more time to complete one oscillation. So clock loses time, and loss is half alpha. Obviously you are taking mod, so mod will become theta minus theta c per second. If they ask per day, multiply by 24 into 3600 seconds. This is the value. And if you use it in temperatures less than the calibration temperature, then what will happen? The time period will decrease, because length will decrease, so time period will decrease. If time period decreases, means the clock will move faster. So faster, so gains time. So gain in time per second, this value will become half alpha delta theta. Now mod we have to take, obviously it will become theta c minus theta, because always you have to take the magnitude. So we will write half alpha theta c minus theta per second. Clear? So these were some applications, important applications. One more application, they ask if thermal expansion is fully restricted, thermal expansion is fully restricted, then a stress develops. So thermal stress we will take, if we are taking in case of rod, we take it as y alpha delta t or delta theta approximately, and thermal strain will become alpha delta theta, where y is the Young's modulus of the material. This is in case of linear expansion. Now if you restrict volume expansion, then in that case thermal stress will be the excess pressure, and this value, instead of y alpha delta theta, it will become b gamma delta theta, where b is the bulk modulus. Gamma we already know that it is thermal expansion coefficient for volume change, and this will become thermal stress, and thermal strain will be gamma delta theta. If they give you alpha, so remember gamma can be written as 3 alpha, so this can be also written as 3 alpha delta theta. So thermal stress or strain are developed in a body whenever the body is expanding, but due to temperature change, but you are restricting it. So as much expansion is produced by change in temperature, that much compression you are providing by external force, right? If they ask you what is the external force which is providing this stress, so that we can write force is equals to stress into area, and that will be the force which is developed from inside also. Internal force developed is also this. Okay. So this was about thermal expansion in solids. Now next thing we have in liquids. Liquids we will take volume change only. So in volume change only we will write at any temperature V theta is equals to V naught 1 plus gamma theta. So if you want to write for two different temperatures, you will use V theta 2 by V theta 1 is 1 plus gamma of the liquid theta 2 by 1 plus gamma liquid theta 1, and kindly don't use this. You will not use this in case of liquids because gamma is large. Solids is very small. There we can use a binomial approximations and other approximations. Here you won't. You will use this thing. Clear? Now here one important case, we have apparent expansion. When we have apparent expansion, means with respect to vessel. So when a liquid is expanding with respect to vessel, apparent expansion we denote as delta V apparent is nothing but expansion of the liquid minus expansion of the vessel. We write like this. Now how we write this? Delta V apparent is nothing but volume of the liquid initially at 0 degree Celsius into gamma of the liquid apparent, let's call it as, because it is apparent, gamma apparent and delta T. delta V liquid actual, this is volume of the liquid initially at 0 degree Celsius into actual gamma of the liquid into delta T, and volume of vessel change, initial volume of the vessel into gamma of the vessel into delta T. So this expression you will use to find the apparent expansion. Now here we have an important case. If suppose initially the liquid was completely filling the vessel, suppose V0, then both sides V0 will cancel, and you can see delta T also cancels. So gamma apparent, we use a direct formula, gamma real of the liquid minus gamma vessel. Gamma liquid is fixed for a liquid, gamma apparent changes from vessel to vessel, and gamma vessel can be written as 3 times of alpha of vessel. So you can use directly this, understood? And if this case occurs, then whatever the delta V apparent value comes in this case, when you have this case, delta V apparent, which can be written as V0 gamma apparent into delta T, suppose it was initially completely filled to the brim. Now this is the expansion with respect to vessel. So where will the extra expansion go? It will overflow. So this will directly give you volume of liquid overflown. When you rise the temperature, the volume of liquid overflown from the vessel will directly become this much, V0 into gamma apparent into delta T. Got it? Now apart from this, we have in gases, expansion is very large. When you are having real gases, directly you will use same V at any temperature, gamma of the gas theta 2 1 plus gamma gas theta 1. Obviously this is large, so you can use this to relate volumes. Now if it is an ideal gas, then in that case we directly go by ideal gas equations. For ideal gas, how to find this value? If we have pressure is constant, suppose pressure is constant, so we know volume is directly proportional to temperature. So we can use Charles' law, V1 by T1. T1 can be written as, because that Charles' law is in Kelvin, so you have to convert in Celsius. V1 by theta 1 plus 273 is equals to, suppose you are taking theta 1 as theta, so it would be better to write V theta by theta plus 273, and suppose I take another temperature as 0 degree Celsius, so V0 by 0 degree Celsius means by 273. We can write like this. So for this, if pressure is constant, we can use V theta is equals to V0 1 plus theta by 273. So if you compare with the standard term, we get one important term, delta V by V0 delta theta. This value we will give a name, we will call it as gamma V, which is called as volume expansivity of any ideal gas at constant P. So this value we will get, if you compare, we will get 1 by 273 per degree Celsius. So for an ideal gas at constant pressure, we get the volume expansion coefficient as 1 by 273. Now same thing, if we apply volume is constant, we know pressure is directly proportional to temperature. So in that case, pressure we can write at theta degree Celsius, P theta is equals to P naught at theta degree Celsius. P P at 0 degree Celsius into 1 plus theta by 273. So here 1 by 273 per degree Celsius is called as pressure expansivity of ideal gas at what? Constant volume. So at constant volume, ideal gas has a pressure expansivity of 1 by 273, and any ideal gas at constant pressure has a volume expansivity of 1 by 273. These are two very important values. Is it clear? One more important thing that we will see from here is, in general, for an ideal gas, if they ask you gamma, this is not that adiabatic constant, this gamma, which is fractional change in volume per unit change in temperature, is found as shown. They will give you a process example. They give you a process where P is directly proportional to T square. This is a process given for ideal gas. You have to find dV by V dt. So how we find this? Let's see. So when P is given, we can use PV equals to nRT. So just try to convert pressure. You can see it is proportional to T by V. So from here we can take T by V proportional to T square. One term cancels. So that means V is proportional to T to the power minus 1. Clear? V is proportional to T to the power minus 1. Or you can directly substitute the expression. So V and one term cancels. So we have got T by V proportional to T square, which I said is TV is constant. One T cancels, so TV is constant. Now you can differentiate it because we want dV by V dt. So just differentiate both sides with respect to temperature. So if you differentiate both sides with respect to temperature, here we will get 0. So first you will put dt, T constant, you get dV by dt. Plus now you take V constant. So we have dt by dt, which is 1, is equals to 0. So from here dV by dt can be written as minus V by T. So we are interested in finding the value of gamma. So you can see from here gamma, which is dV by V dt, this will become minus 1 by T. That's it. So in this way we can find the expansion coefficient for gases. Understood? So when we are given ideal gases, we can solve the questions in this particular way. So that will be all for this lecture. Other things we will discuss in the next class. Okay, thank you. How much time?
1 hour.